Okay, in this video, we'll be looking at graphing sine and cosine. So what I'm going to start with is a typical unit circle. And the first thing you'll notice is that I have a few extra lines than I typically would have. What I've done is I've broken my circle into equal parts. And the equal parts will be in parts of pi over 12, as opposed to just putting pi over 6, pi over 4, pi over 3. So each line here represents 1/12 pi of my entire circle. So as I go around, 19/12s, 20/12s, 21/12s, 22/12s, 23/12s, and of course 24/12s puts me at 2 pi. And by divvying up the circle equally, it'll help us in creating the graphs of sine and cosine. So I start with my circle all divvied up. And what I'm going to do is unwrap my circle. So as I unwrap it, the circumference around the circle, where I had all of my angles labeled, become a horizontal axis. So I'm going to be able to create now essentially a Cartesian plane, where I have a horizontal axis, which would have come from the circumference around the circle, and my vertical axis will come directly from the circle itself, where my middle number is 0, my height up top is 1 unit, and below is -1. So now what I have is essentially a Cartesian plane. I'm going to duplicate this Cartesian plane because what I'm going to do is I'm going to plot on one Cartesian plane my y coordinates, and on the other I'll plot my x coordinates at each one of the different radian amounts. The top one, because I'll be plotting my y coordinates, that one will wind up being the graph of y equals sine theta. And here will be y equals cosine theta, because we saw earlier that in our unit circle, the y coordinates at each angle was wound up being the value for sine, and our x coordinates wound up being the values for cosine. So here we go. I'm going to start at 0 pi. The coordinates at 0 pi are 1, 0. So if I was to actually show how long my 1 unit is, now I have something physical that I'm going to move to my different Cartesian planes. So the first point, I'm plotting my y coordinate. The y coordinate was 0. Here, the x coordinate is 1. So I'll show that I'm actually putting the length of my horizontal leg, my horizontal distance, actually on the second plane. So I'll continue this as I go around the circle. Now I'm at pi over 12. If I was to project a triangle from pi over 12, I'll have a vertical amount and a horizontal leg. Those legs, the blue leg and the green leg, actually represent the actual coordinates. So I'll transfer those onto the different Cartesian planes. So there's my y value, and there's my x value. And notice with here, I'm not having to rely on actual values for my coordinates. By using the visuals, I can actually take the actual lengths of those sides and begin to plot it. So I'll continue around. Next, I'm at pi over 6. I'll draw my triangle, and I'll transition my legs. There's the value for y. There's the value for x. Continue around, pi over 4, transition, transition my horizontal. You're beginning to see a pattern occur. So we're at pi over 3, transition my vertical leg, my y coordinate, transition my horizontal leg, my x coordinate. And so as I continue around, the pattern continues. There's my vertical, there's my horizontal. Now what's counterintuitive is that though I'm plotting it vertically, these actually represent the horizontal distances. So as I continue, pi over 2. Well, pi over 2, the coordinates are x for 0 and y is 1. So there's my y value 1 and x is 0. Now as I go around, there's something to be careful now. Yes, my vertical amount, y, continues around, but because the point is actually in quadrant 2, this is a negative value. So I'll represent that by placing it underneath the horizontal axis to show that this value here is negative. So I continue around, transition to vertical, transition to horizontal, and again it stays underneath. Same thing across. There's my vertical, there's my horizontal. Next point, 5 pi over 6. There's the vertical, there's the horizontal. Couple more points, 11 pi over 12. Vertical is getting closer to the axis, while this is getting further from the axis. And now that we're at pi, there's our vertical, the horizontal, and of course, y actually equals 0. Now that we've transitioned to quadrant 3, all of our values are negative. So I'm showing my vertical is below and my horizontal is also below. So as I continue across, values transition. 5 pi over 4 transitions next to 4 pi over 3. There's my vertical. There's the horizontal. We're beginning to see a more clear pattern now. Vertical, there's my horizontal. Now we're at 3 pi over 2. And of course, the other value is 0. Last quadrant. So now that we're in quadrant 4, the y is still going to be negative, but now the x is positive. Coming across, 5 pi over 3, transition, and we're almost back. There's a 7 pi over 4, transition it, while the horizontal. Next, 11 pi over 6, transition to vertical, transition to horizontal. 23 pi over 12, there's my vertical, there's the horizontal, and we're back at 2 pi, which have the exact same coordinates as 0 pi. So when we look at these patterns that occur, now mind you, the graph is not the lines. The lines just help us determine the distance that the actual coordinates are. So really the points are at the ends of these segments. So if I connected all of the different points, then I get this nice smooth curve. This is actually the graph of y equals sine theta. And if I did the same thing at the bottom, now we have the graph of y equals cosine theta. So they take on very consistent characteristics. They look very similar. The difference is really where one begins and the other one begins. So when we put this all together, y equals sine x looks something like this. And it does go on forever. I only went around the circle starting 0, going in a positive direction to 2 pi. I could have started at 0 pi and gone in a negative direction and continue around the circle. And y equals cosine x, same situation. So here are the graphs of sine and cosine.